So this is the molecule that I will be dealing with today. And first, we're going to be starting off by drawing the Lewis dot diagram for this. So our central atom is going to be krypton. And then we have the 4 surrounding atoms of fluorine. And I have a non-octet molecule. By looking at it, our central atom is a noble gas, and looking at the rules for it to be a non-octet molecule, the central atom has to be either a noble gas or a halogen, and this is a noble gas. So by that, I already know that I'm gonna have singular bonds all the way around, and then I draw the dot around the surrounding atoms as such. So now I want to calculate if I have any electrons left over. So we're going to calculate our half number, which is, we have 8 kryptons, plus we have 7 fluorine, but looking at our subscript here, we have 4 in the molecule. So we're going to multiply this by 4, so then equals to 36. So now we look at the bonds here, and of course we always have 2 of these connecting. So we subtract the bonds first, which gives you 28. And then counting the number of electrons on the surrounding electrons, we have 24, which that leaves you with 4 electrons. So now we're going to draw that into our Lewis dot diagram. So 1, 2, 3, 4. So you can draw it anywhere, but drawing it there for now. And this is the Lewis dot diagram for this molecule. So now we're going to write out our condensed electron configuration for the central atom, which is krypton, and the closest noble gas to krypton is argon. When doing the condensed version, I can just jump straight in to the 4th energy group, and we have 2 of the s orbitals, and then we make it past to 3d, and we go past 10 of them. And then we go to 4p, and we go past 6 to get to krypton. So I already set up my graph for the configuration. So now we're gonna use our condensed electronic configuration that we found to create the diagram. So first off, we're going to put argon in the s orbital, and then we're going to set up our s orbital as such, and just going to be setting up the other orbitals as well. So now, using my electron configuration up there, we have 2 electrons in the s orbital. So we're going to draw one going up, so going clockwise, and then one going down, going counterclockwise as such. So now we're going to fill in the d orbital. So we have 10 of those, so we're gonna use all 10 of these. So first, I'm going to draw in the singular electrons in these orbitals. And the singular electrons first are going to be going up clockwise. Now we're going to go back in and fill in the electrons going downwards, because we have 10 of the electrons, so we're going to be filling up all of them going counterclockwise. And we're going to do the same thing for the p orbital, and we have 6 of those. So this is the condensed electron configuration for a diagram for krypton. So now we're going to make our hybridization diagram. But first we have to figure out what type of bonds we have from our Lewis dot diagram that we drew before. So these are bonds, but we have to differentiate if they're CCB bonds or if they're sigma bonds. And we look at that by looking out at our surrounding atoms, which has 1, 2, 3, 4, 5, 6 electrons. And if we look at our periodic table, we can see that fluorine has 7 electrons. So we know that it doesn't fit the criteria of a CCB bond. So by default, these bonds are all going to be sigma bonds. And we have 2 lone pairs that we have to take into consideration. So here we have 2 lone pairs. So now to show hybridization, I will extend a line as such, and then write hybridization on top. And now we're going to jot down what types of bond we have underneath. So we have 4 sigma bonds, and we have 2 lone pairs. And I drew my graph down here because I did not have enough space. So now I just set up my orbitals, and I have 6, counting for the total number of bonds I have here, which will be our number of electrons that we have here. So now we gotta draw in the electrons. So we have 4 sigma bonds, and that counts for 1 electron per orbital. So all we have to do is just draw 1 electron going clockwise upwards as such. And we have 4 of these as such. And now we're going to draw in the lone pairs, which counts for 2 electrons per orbital. And we have 2 of these as such. And now we have to name this, all of this. So we want to look at which orbital that we're in. And as you can see here, we are in the 4th orbital. So we're gonna put 4 in front, as that's the energy group that we're in. And then, as you can see here, kind of in the bottom, I kind of made these lines representing the s orbital, p orbital, and d orbital, and taking the total number of bonds that orbitals that I have here, and then checking it off. So 1, 2, 3, 4, 5, 6. So I have 1 s, 3 p's, and then 2 d's. And that's how you make the hybridization diagram. And now we're going to be drawing our 3D shape for this molecule. So we have 6 electron groups here. So down here, we're going to be writing that in. So therefore, geometry equals square by pyramidal, and make sure to write that you have 2 lone pairs beside the 6 electron groups to specify that you do have 2 lone pairs counting for the 6 electron groups. So as we learned, putting it on the top and the bottom gives the electrons the most space when it comes to this molecule. And we have 2 lone pairs for it. So now let's try it. So we're gonna have our lone pairs on the top and bottom, as it gives it the most space. And then we're gonna have fluorine going into the paper. And then we're gonna have 2 fluorines going out of the paper, find the 3D shape. And now we have to write our therefore statement for the final shape and angle. So shape equals to a square planar and angle equals to 90 degrees. And as we learned from before, that when you have lone pairs, you always have to subtract 2.5 for every lone pair that there is. But for this one, it's a special case, as when you have electron repulsion equally on the top and then electron propulsion here equally at the bottom, these surrounding atoms will not move this way nor move that way. It'll stay constant here, 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 not really changing it. So the angles won't really change, and it'll be 90 degrees, as we'll draw it here as such. And that's the Vesper theory for this molecule. So the intramolecular bonds that krypton and fluorine have between each other is an ionic bond, as if you look at the electronegativity between them and you subtract it, it'll give you an ionic bond. And the fluorine has a higher electronegativity than krypton. So because this has more pull, this becomes a partial negative, as it's gaining more electron by taking it. And the krypton will have a partial positive as it's losing. So this partial positive will be attracted to, say, another fluorine that is partially negative. And that fluorine is connected to, say, another krypton that is partially positive. So this creates a dipole-dipole bond between like two molecules, such as this. And if we look at water, we know that between hydrogen and oxygen, they have a very high difference in electronegativity, and this is what's known as a hydrogen bond, as water will be much more positive and the oxygen will be much more negatively charged. So this water will have a much forceful pull on another water molecule. And hydrogen bonds are the strongest bonds, so it's much more difficult to break those bonds. So comparing this molecule to water, this has a much more lower melting point than water. And considering that it's much more lower, it would easily turn into a gas state compared to water, which is a liquid.